Hello. Today we will talk about a group called binary octahedral group, and this group is the starting point of the paper. The binary octahedral group is denoted by 2O, and this group is a double cover of the familiar octahedral group denoted by S4. To understand this, let us discuss what the double cover means in this context. So I have a matrix H shown here. This matrix is constructed with three real variables. You have X, Y, and Z. And the matrix is Hermitian. So you have H dagger equal to H, and it is traceless. Trace of H is 0, and trace of H dagger H equal to X square plus Y square plus Z square, which is nothing but the square of the length of the vector. So X, Y, Z are three real numbers, so they can denote a vector in three-dimensional space. Now I'm going to apply a transformation on H given by H going to U dagger, where U is a special unitary matrix. It is easy to show that under this transformation, the 3 points I made earlier, that H is Hermitian, it is traceless, and trace of H dagger H is the square of the length. These three conditions remain invariant. And in fact, this transformation corresponds to a rotation of the vector xyz in the three-dimensional space. And as a result, we have correspondence from the special unitary matrices to special orthogonal matrices in three-dimensional space. This mapping is a 2-to-1 mapping because plus U and minus U, both of these SU2 matrices map to the same SO3 matrix. That is why we call this a double cover. So SU2 forms a double cover of SO3. Now these things are the continuous groups SU2 and SO3. We are interested in finite groups. So for that, think about the discretization of the sphere, because sphere corresponds to the group SO3. When we discretize a sphere, we obtain the platonic solids. We have 5 platonic solids, and corresponding to these platonic solids, we have 3 finite groups: a tetrahedral group, octahedral group, and icosahedral group. Now, as we saw here, there is a correspondence between the SO3 and SU2. So when you discretize this, there should be also a discrete version in the space of SU2. So these groups are the binary groups. So this is their origin. The tetrahedral group is a finite subgroup of SO3. Correspondingly, we have the binary tetrahedral group, the finite subgroup of SU2. And in the similar way, we have binary octahedral group and a binary icosahedral group. In my construction, I am using the binary octahedral group. The reason for that will become clear at the end of this video. Now, I generate this binary octahedral group using these two 2x2 matrices, bold T2 and bold R2, where tau and tau bar are the complex 8th roots of unity. So throughout this paper, I use bold lowercase letters to denote matrices. Here we have bold T2 and bold R2. And if we use these two generators, we obtain a group of 48 elements, and that forms the binary octahedral group. And this particular representation, the doublet representation, I call it _2. The abstract group elements corresponding to these T2 and R2, I call them bold T and bold R. I use bold uppercase letters throughout this paper to denote abstract group elements. To see how the binary octahedral group is related to S4, we take the tensor product of these doublets. So this is shown here. Underscore 2 cross underscore 2 gives you a 3 plus 1. This is exactly how we take the tensor product of the SU2. You have the tensor product of two doublets that gives you a real triplet and an invariant singlet. The symmetric part goes to the triplet and the anti-symmetric part becomes the invariant singlet. Here I show the symmetric part which forms the triplet. So we start with two doublets x1 x2 and y1 y2 which transform as underscore 2, and the symmetric parts shown here are the first one x1 y1 plus x2 y2, the second one minus I x1 y2 plus x2 y1, and the third one I x1 y1 minus x2 y2. And this forms a specific basis, and the significance of that will become clear at the end of this video. And if we use this basis, then the generators T and R turns out to be these 3 by 3 matrices. And these 3 by 3 matrices are nothing but the generators of the group S4. In this way, we can see how the generators of 2O give you the generators of S4. The group S4 is extensively used in model building, and almost always the group is constructed with 3 generators S, T, and U. On the other hand, here I am using only 2 generators, T and R. The minimum number of generators needed to construct S4 is just 2. In the literature, we see 3 generators because that makes it convenient to show how the symmetry is broken. But in this paper, for the purpose of brevity, I would like to use just 2 generators, T and R. The relationship between these generators and STU is given in the appendix. I will show you that. The conversion is given here. S is given by R square and U is given by TR square T square R. If you look at the triplet, we get S as diagonal 1 minus 1 minus 1 and U as this one. And these are the familiar generators that you see in the literature. We can also look at the presentation of group S4, equation A2 here. TR square equal to T cube equal to R to the power 4. And all of them are equal to 1. So if we have generators like this, it would generate S4. And let's compare this with that of binary octahedral group. It's very similar. As you can see, TR square equal to T cube equal to R to the power 4. However, we have to do one more squaring to get 1. So in other words, here I have shown T to the power 6. We can also have R to the power 8 or TR to the power 4, which would give you 1. So there is this additional square that is required. This is nothing but a Z2 group that corresponds to the double of the double cover. This Z2 group form a normal subgroup of 2O, and if you take the quotient of 2O with this Z2, we will get nothing but the group S4. Now let us look at the character table. The first 5 irreps are nothing but the irreps of S4. You have 2 triplets, 3 and 3 prime, a doublet 2, an invariant 1 and another singlet 1 prime. If you look at the conjugacy classes, we see some of them with a minus. So you have the trivial one with a trivial minus, a 3 cycle, minus of 3 cycle, 4 cycle, minus of 4 cycle. These two don't have that. And for the first 5 irreps, which are the irreps of S4 also, the conjugacy classes with and without the minus are equal. For example, the 3 cycle 1, 2, 3 and 1, 2, 3 minus, they contain exactly the same group elements. On the other hand, the last 3 irreps, underscore 2, underscore 2 prime and underscore 4, they are faithful irreps of 2O. There are 48 distinct group elements for these irreps, and 24 of them are minus of the other 24. And when you have these two conjugacy classes with and without minus, one of the group element belongs to one conjugacy class and the negative belongs to the other. That is how the group elements are distributed. And in the last two conjugacy classes, the group element and its minus both belong to the same class. Now I will go back to page 2 and show you how some of these irreps are explicitly constructed. The irrep 2, which is also an irrep of S4, is constructed using the matrices bold omega 2 and bold sigma x. These two matrices correspond to the generators T and R. And omega bar and omega are complex cube roots of unity. As you know, the doublet of S4 is a real irrep. Here we have used complex numbers to construct the matrices as a matter of convenience. We used underscore 2 as the defining representation of 2O. As we saw in the character table, 2O has two more faithful irreps given by underscore 2 prime and underscore 4. They are constructed in this way. Underscore 2 prime is constructed by taking the product of underscore 2 and 1 prime, and underscore 4 is constructed by taking the tensor product of 2 and underscore 2. The generating matrices of the irrep underscore 4 is given here. The first one corresponds to T and the second one corresponds to R. Here on the left side, I have the Kronecker product of bold omega 2 and bold T2. Throughout this paper, I use the symbol O times to denote both tensor product like here and also Kronecker product like here. So from the context you can understand what it means. This is the Kronecker product of the 2 by 2 matrix bold omega 2, and bold T2 is nothing but the matrix we used in defining O2. So that's the Kronecker product is shown here, and this is in fact a 4 by 4 matrix. Its full expansion is shown here. Similarly, the second generator is obtained by taking the Kronecker product of the polymatrix and bold R2. Bold R2 is the generator of 2O defined previously, and we have the 4 by 4 matrix whose full expansion is given here. I use Kronecker products at several places in this paper. It's brief in that way, so you can always expand it and see the full expression if you would like to. Let's say we have a doublet 2 given by x1 x2 and underscore 2 given by y1 y2. Then the tensor product of that is nothing but x1 y1 x1 y2 x2 y1 x2 y2. This is the irrep that transforms as underscore 4. Now I will tell you how the binary octahedral group is relevant in constructing the neutrino models. For that, let me go back to the Hermitian matrix and the action of unitary matrices on it, where I showed that SU2 is a double cover of SO3. Now, this can be shown in a different way. So instead of the Hermitian matrix, you start with a symmetric matrix S. This matrix is also constructed with three real variables, phi1, phi2, and phi3. And the matrix has the following properties. It is symmetric, so S transpose is S, and its dagger is equal to I sigma y S I sigma y transpose, and also the trace of S dagger S is the square of the length of the 3 vector, phi1 square plus phi2 square plus phi3 square. So these relationships are there, and then on this matrix S we apply a unitary transformation S going to U as U transpose. Earlier it was U dagger for the case of the matrix H. Here for the symmetric matrix, the transformation is given by U as U transpose, where U is a SU2 matrix. So you can show that under this transformation, the earlier three properties of the matrix, that S being symmetric, S dagger is I sigma y, S I sigma y transpose, and trace of S dagger S is square of the length. So these things remain invariant, and therefore this transformation also corresponds to a rotation in three-dimensional real space, and it demonstrates that SU2 is a double cover of SO3. Now let us look at the structure of the symmetric matrix S and compare with our tensor product expansion equation number 4. The first component is x1 y1 plus x2 y2. That goes along the trace that corresponds to phi1 here. The second component is minus I x1 y2 plus x2 y1. It is the off diagonal part, and that you can see that it corresponds to phi2 here with this I. And the third component is x1 y1 minus x2 y2. It is also in the diagonal, but it is traceless part, and that with an I, and that corresponds to this phi3. So basically this tensor product expansion directly relates to a 2 by 2 symmetric matrix. So if you take the right-handed neutrinos as a doublet, then you can get the Majorana mass matrix, which is a symmetric matrix, and its components being the triplet phi1, phi2, phi3. So this is the significance of using 2O to construct the model. Why did I specifically choose a binary octahedral group, not any other binary group? That's because I had a paper in 2019, which I talked about in the previous video. Let me show you that. The paper was based on S4, and it contained a triplet with a vacuum alignment minus a minus 2 root a and a, and this model led to sine theta 13 is 1 by root 3 sine pi by 12, and this is an excellent agreement with the data. I constructed this vacuum alignment by extending the group S4. The extended group was a bit cumbersome, and also the model has the problem of cross terms. So as soon as you consider the cross terms, the vacuum alignment is spoiled. So my main motivation was to improve this previous paper so that I can have a model with a more elegant group and also I don't have the problem of cross terms. Initially, I worked with right-handed neutrinos transforming as a triplet of S4. So you have n times n, which would give me 1 plus 2 plus 3 prime plus 3, and this is the symmetric part, and this 3 prime directly corresponds to the vacuum alignment that I mentioned earlier. I could not make any progress after working for many months. So then I decided that maybe I can take the right-handed neutrinos as doublets of the binary octahedral group, so that the expansion would be nothing but 3 plus 1, so that the construction would be easier. That was my motivation. Another thing I would like to point out is that the eighth root of unity tau, as well as the cube root of unity omega, naturally occurs in the construction of the binary octahedral group. I thought that having this eighth root of unity and cube root of unity could be the way to reach pi by 12, which corresponds to the product of these two roots of unity. Finally, I would like to give you a general motivation for going in this path. Initially, in the literature, we used A4 and S4 to construct flavor models, and these gave tri-bimaximal mixing. And when we looked beyond tri-bimaximal mixing, we wanted to get small reactor mixing angle. That would require a group with a finer discretization. That is why in the literature you see groups like delta 3n square and delta 6n square, which divides the transformations into finer discrete pieces. Now, taking the double cover is another kind of a finer discretization, but this is a different kind in the sense that here we are sort of looking like taking the square root of a group rather than splitting it into smaller divisions. This is a path which hasn't been explored, and I believe that a lot more interesting phenomenology could be found out if you follow this path of group extension. Thank you very much. See you soon in another video.